Can anybody tell me what a simple machine is?
I'm gonna take a wild guess. Is it a machine that's simple?
So yeah, it is a machine that's simple, and by that we mean it doesn't have a motor, an engine, anything like that. Uh, does anybody know like one type of simple machine they could throw out there? No. Okay, well, you guys know these. I know you know them. So, like for example, one type of a simple machine would be a pulley. Another type is something called an inclined plane. We usually call it a ramp, right? Levers. Levers are simple machines. This is a wheel and axle. That's a simple machine. So there's actually six. We'll write them all down here real quick, just so that you guys have them. Oops. So pulleys. And I think you guys know what a pulley is, right? Um, it's a wheel that spins, and you can put a rope around that wheel. Um, Inclined planes, or you could just write ramps, right? Levers. So this is a lever, like a seesaw is a lever, a crowbar is a lever. Wheel and axle. Oops. It would help if I put an X instead of an L there. So wheel and axle, and this is a wheel and axle. Think of your doorknob. Your doorknob's a wheel and axle. You have a big knob, and then there's a stem behind it. All right, and then we have screws. A screw is actually a simple machine. It's what it is. It's an inclined plane that's wrapped around a cone, and yeah, believe it or not, they actually do make your work easier. Okay. And then the very last one, which is also just a variation of an inclined plane, is a wedge. So an axe is a wedge. It's a moving inclined plane. So those are the six basic ones. So now that you know what they are, and they are simple. They're machines that are simple. They don't require any motors, engines, nothing like that. Why would I use a simple machine? Like why would I use a ramp? And I could tell you, I'll even give you an example. All right. Whenever I get to take a group of students anywhere, which this year has been never, but usually we go to lots of places. So whenever I get to take a group of students somewhere, when we're going into a building, if there's a ramp, like a big chunk of people will walk all the way out of their way and walk up that ramp instead of walking up the stairs. Like, why would you do that? Stairs are right in front of you. Instead, they'll go over and walk up the ramp. My son does it too. So why do you guys do something like just tell me? Just tell me like why do you do that?
It's easier.
Yeah, okay, yeah, it's easier. But it's easier in what way? Like I just told you a lot of people will go out of their way. So there's more time involved, right? So even though there's more time involved, it's still easier. And it's easier how? Can anybody explain that to me? Easier on your what?
It's not as steep as stairs.
Okay, so it's not as steep. That's totally true. And so it's actually requires um, less effort by your muscles, right? It requires less force. And so that's why you guys do it. Um, so simple machines, this is what they do. They either redirect a force or they multiply a force. So if I use a simple machine, I can actually do a task with less force. Or I can do a task um, in an easier way because I can redirect the force. So just thinking about redirecting the force, for those of you who like you either know people who have horses, um, you've driven by farms, right? I know lots of you have relatives who have like ranches and stuff. Um, on old barns, they always have like this beam that sticks out, and there's a pulley on top of that beam. I don't know if you ever thought about what that pulley was for, unless you had to use it. You know, I grew up in the country, so I've had to use these before. Um, what you do with that is you put a bale of hay, and then you pull the hay. You run a rope around a single pulley, and then you pull the hay up by you pulling down. The alternative, you guys, to getting the hay bale up into the attic here area of the barn where you store it is you take the hay and you walk it up a whole bunch of stairs. Now that's very tiring. The reason that this is easier is that I can actually use my body weight, right? Like I can pull down, use gravity to help me, use gravity to, use my weight, and then go back up on the rope and pull again. All right. So this is a single pulley. This is an example of redirecting the force. And if you've ever had to do that work, you know also that you don't want that hay or straw, depending on what you're doing. You don't want that next to you all the time. It's like insulation, super itchy. So you definitely don't want to be walking these bales up a whole bunch of stairs, right? And then in this example, here's someone installing a motor onto their boat. Now this motor, they're heavy and you may not be able to lug them around. So I don't know if you can see this, but he has a system of pulleys. So on each end here, there's 2 pulleys, and he has a rope wrapped around all of those pulleys and then onto the motor. So what that does is it multiplies his force. So this motor the motor may weigh like 400 pounds. He only has to pull with 100 pounds. All right, so it multiplies the force. So those are the 2 things that simple machines do, either redirect or multiply an input force. So if we go, how does the simple machine multiply the input force? Okay, this is how it works. If there is no friction, we talked about this before. If there's no friction, then the work that I put into a machine is equal to the work that I get out. It's sort of like the energy you put into something is equal to the energy you get out of something. This is because of the law of conservation of energy. Remember we said work done equals change in energy? Do you guys remember? Like this all kind of comes together here. So assuming there's no friction, the work that I put in to using the machine will be the work that I get out from the machine. Do you remember that work is force times distance? It's actually force times displacement. We're just going to say force times distance. I think everybody is okay with that, right? Yeah, okay. I see a few nods. All right. So, so what that would mean, you guys, is that the input force, so the input side is your work, All right. Input, the input side is your work. And then the output side is what the machine does. Okay? So in this example, I'm going to go back really quick. In this example here, the input side would be this hand pulling. So the force of this hand and then however far the hand had to pull. The output side would be the weight of this motor times however high it got lifted. Does that make sense to you guys? Yeah? Okay, I saw some nods. I saw a lot of blank stares, but I'm seeing more nods. All right? Okay, so so far, right, we have force input times distance input. That has to equal force output times distance output. Now, I'm using the machine because it multiplies my force, right? And it multiplies, if you can look at this equation, it's multiplying my force because of something specific. So if I want this F to be little, right? And I want this F is going to be bigger. Like this is the weight of a motor. This is me applying a force to lift that motor. So if I want this F to be smaller, my input force to be smaller, then what has to be bigger? My input distance. And the output distance will be smaller. So I want you guys to think about this for 1 second. Think about walking upstairs versus walking up the ramp. If you walk upstairs, like let's say it's walking up into West Leiden. I'm trying to think of how many, are there like 6 stairs, do you guys think? Maybe to walk an entrance to? Does that seem about right? 5 stairs, 6 stairs? We'll say it's 6. So those 6 stairs are probably, you only have to walk up like 4 feet, right? So you're only lifting your body up 4 feet if you walk up the stairs. If you walk up the ramp, do you have to walk only 4 feet or do you have to walk a way bigger distance? You have to walk a way bigger distance, right? So because the distance when you use the machine is so much bigger than when you don't use the machine, the force is so much smaller. So I'm increasing the distance that I have to apply the force over when I use the machine so that I can decrease the force. So that's how simple machines work. Like let's look at an example right here with this box. So I have a 2 meter long ramp and the ramp is 1 meter high. Now I have 2 options. I could either take a box and I could lift it up, right, 1 meter to put it in its spot, or I could take that same box and I could push it up the ramp 2 meters. Now, I might choose to push it up the ramp. I might choose to lift it. I don't know. But whichever one I do, you guys, the work is going to be the same if there's no friction. So I'm going to say, I'm going to write this out here. So work using well, actually here. Let's not do it that way. Let's just do that equation that we had. The work input times the distance input. Oh, did I say the work input? I meant force. Sorry. So the force input times the distance input. You know what? I have to change my line weight to make this visible. Is equal to the force output times the distance output. All right? Now, using the machine is the input side. Not using the machine would be the output side. All right? So let's figure out what would be the force necessary to slide this block up this ramp. Okay? So that would be the input force. How hard would I have to push to slide the block up the ramp? Well, if I was sliding the block up the ramp, I would have to push it 2 meters, right? If I'm not using the ramp, I would have to lift this block, and it has a weight of 10 newtons, so I would have to apply a force of 10 newtons, and I would have to lift it 1 meter. All right, so now I have force in times 2 equals 10 times 1. You guys know that's 10, right? And then how would I get rid of the 2? It's being multiplied, so I would divide. Those go away, and the input force would be 5 newtons. So if you look, you guys, if I didn't use this machine, I would have to apply a force of 10 newtons. Now I did use the machine, so I only have to apply a force of 5 newtons. Now why was the force half? The force was half because the distance was double. Okay? So simple machines make your work easier by increasing the distance. So they make your work easier by basically, or did I say increasing the distance? By increasing, blah, 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 blah. By decreasing the force required. Decreasing the force required also requires that you push that force for a longer distance. So anytime you use a simple machine, it will take more time than if you didn't, because you have to move your force over a bigger distance. It takes more time to walk up that ramp than it does to walk up the stairs. But the force required is less to walk up the ramp. Now, does everybody have this? Can I go on to my next slide? I'm looking at people's faces. Most people are looking up. Okay. So, well, and just so you guys know, there are some examples on our website, but they require Flash, which on your Chromebook may or may not work. All right. So you guys know, once again, this is just review. So the work input is the work output. That's if there's no friction. And that's the best case scenario. So once again, the reason you use the machine is because it lessens your force. It lessens your force. The input force is going to be a lot smaller than the output force. Why that symbol is turned the way it is, I don't know. It's backwards, right? So the input force is going to be less than the output force. That's why you use a simple machine. Do not ever tell me you use a simple machine because you're doing less work. Are we doing less work by using the machine? Yes, no. So are we doing less work by using the machine? You guys should be telling me like no, right? They're equal. You're doing the same amount of work, the exact same amount of work, just applying less force. Okay. So how effective are simple machines in the real world? Well, in the real world, you guys, there is friction. So in the real world, the input force or the input work is not going to equal the output work, right? To fix that equation, to make it more realistic, what we always have is a percentage of the work that I put into the machine actually comes out of the machine. So we would say the efficiency times the work in is equal to the work out. We will always have to put more work into the machine than we get out. So in real life, when you use a simple machine, you're doing more work, expending more energy than you would if you didn't use the machine. But once again, then why use them? We use them because they lessen the force. There are things I can do with a simple machine that I can't do in real life. You know, if you've ever, has anybody here ever used a hammer to pull a nail out of a piece of wood? You know, the claw, the back claw. So I saw some nods and some yeses. All right. So if you use that back claw to pull a piece of, or to pull a nail out of wood, you've used a lever. That's a simple machine. Okay, it's kind of like a crowbar. That's something that you can't just do normally. So I can't. I mean, I'm pretty strong, but I can't grab a nail and pull it out of wood. Just not possible, right? But I can use the back of a hammer and use it as a lever. So that's why you use the simple machine. You use it because it lessens the force, lets you do things that normally you can't do. You don't use a simple machine because it lets you do less work. Okay, it's not why you do it. All right. So now there's something called mechanical advantage. What mechanical advantage does, you guys, is it tells you how much the machine, without friction, how much the machine multiplies your force. So does it double the amount of force that you put in? Does it triple the amount of force? And there's two different ways that you can calculate it. So TMA is what we call theoretical mechanical advantage. All right? So the theoretical mechanical advantage tells you, in theory, without any friction, how much will my force be multiplied by? And you would take the input distance and divide it by the output distance. If I double the distance that I have to apply the force, it doubles my force. If I triple the distance, then it triples my force. Then AMA is actual mechanical advantage. And that tells you, even with friction, how much your force was actually increased by. So that would be the output force divided by the input force. So if the output force is twice as big as the input force, it doubled my force. If the output force is 3 times as big as the input force, it tripled my force. So TMA, once again, TMA is telling you, if there's no friction, this is how much your force will be multiplied by. And then AMA is telling you, this is how much my force was actually multiplied by. So when are they the same? I basically just told you. When would they be the same? Should I pick someone and ask him? They're the same when there's no what? It's the F word. No.
Friction.
Yeah, no friction. Thank you. All right. So when there's no friction, then these two things are the same. When there's friction, the actual mechanical advantage will always be smaller than the theoretical. So this one will always be the smaller one. This one will always be the bigger one. If there's no friction, they can be the same. Okay. Now, just to let you guys know, you don't write this down. I'm just kind of showing you. This is kind of showing you the different distances when we look at it. But let's if we're going to determine mechanical advantage for a lever, just so you know, the input distance is the distance that runs from the fulcrum to the edge of the lever, and the output distance is the distance that runs from the fulcrum to where the load is. Now, the fulcrum, you guys, is a pivot point. That's just a fancy word for a pivot point. So for a lever, that is a vocabulary word you need to know. The lever has a pivot point. Think about a crowbar. All right, so I have a crowbar, and it kind of looks like that, right? So this point, that would be the fulcrum. You know, this kind of looks like an old school teeter-totter. Has anybody been on a teeter-totter that didn't have like a spring in the middle of it? That was just a piece of wood, and then there was usually sitting on a metal pipe? Did any of you guys ever get to play with one of those? Yeah? Okay, so a few people. When I was a kid, you guys, we had those on the playground. And it was really actually kind of cool. We all got to learn a little bit of physics in a sneaky way, because in the bottom, on the bottom of the teeter-totter, there used to be this like kind of like a little fixture where you can adjust the size of the teeter-totter. So like if you had me sitting on one of these sides, okay, and then you were sitting on the other side, you could adjust this so that when the bigger person was on one side, they would be on the shorter end. And when the smaller person was on the other side, they would be on the longer end. Because if I have a bigger force, I want a smaller distance. If I have a smaller force, I want a bigger distance, right? So it was very, very cool to grow up with these teeter-totters, because you really understood leverage. Now they got rid of them because, you know, your parents, people in my generation, they're animals and they can't help themselves. So what they would do, not that I'm sure your parents never did this, but what people would do is they would get someone like stuck up here, and then they would jump off of the end so that the other person would slam into the ground, or they would put a person on one edge of this, and then the other person would jump on to try to launch them off, right? So they just decided that was probably not safe, and most places got rid of them. But anyway, if we're looking at the distance, the input distance on the long side of the lever up to the fulcrum, the output distance from the fulcrum to the edge. Okay, so that's with the lever. Inclined planes. With an inclined plane, the output distance is the height, and the input distance is the length. So remember, the input is always the side that you're pushing on. The output is always what ends up happening. So I push something up a ramp, it gets lifted above the ground. For a wheel and axle, you guys, the output distance is the outside, it's the biggest wheel, the radius. Oh, I'm sorry, did I say output? I meant input. So the input is the biggest radius, and the output is the smaller radius. Now, all of you actually have probably used a wheel and axle today. If you were at school, I would say you definitely used a wheel and axle, because I kind of alluded to this before. Your doorknob is a wheel and axle. So I used to live in a really old house. It's like a really old farmhouse. And some of the doorknobs, because they were so old, they would break off. And so whenever that happened, if you closed the door, you'd kind of be stuck. Now, the reason that you'd be stuck, because I don't know if you ever tried, you guys will have to try this at some point today. If you go behind the door and try to just turn the stem instead of turning the handle, it's really hard, right? Like either really hard or impossibly hard to turn it. But it's really easy to turn the handle. Once again, why? Because the handle turns a bigger distance than the stem. So if you don't believe me, like I said, well, even if you do believe me, just try it out today. Walk up to a door and without actually grabbing onto the handle, grab on the backside and try to turn that stem and see if you could do it. It will be significantly harder than just grabbing the handle. Another good example of wheel and axle, you guys, is a screwdriver. If you've ever used a screwdriver, okay, you could either grip the handle and try to turn the screw, or you could grip the stem and try to turn it. I'm going to tell you which one's easier. It's the handle. Why? Because the handle's bigger and it has to move a bigger distance for every one revolution. All right? So the bigger radius is the input distance, smaller radius is the output distance. And then for a pulley, you guys, there are two different ways that you can measure the distance. The input distance is how much string you would pull out. The output distance is how high this lifts. Or, it's actually kind of crazy for a pulley. I could actually just count the number of pulleys, and that tells me the mechanical advantage. So the theoretical mechanical advantage of this pulley system would be 4. So this pulley system should quadruple my force. Or another way of thinking about it is make the force that I have to apply 4 times smaller than what the load is. So let's look at what this looks like in a problem. All right? So before I even do that, here's a summary of all the equations. Now this is posted online if you need to see it. But remember we said efficiency is times work in equals work out, which would basically mean efficiency times the input distance times the input force equals the output distance times the output force. We said theoretical mechanical advantage is the input distance over the output distance. Actual mechanical advantage, the output force over the input force. And then because if there's no friction, AMA and TMA will be the same. If there is friction, the efficiency is the actual mechanical advantage divided by the theoretical. So let's do 2 problems. Like I said, this is all online, but I would put these equations with all of your other equations. Like make sure that everything is written down in the same spot, right? Okay. So let's do 2 sample problems. I'm going to draw this out because once again I like drawing it. It makes it make more sense to me. So I have a crowbar with a total length of 1 meter. So the total length of my crowbar from one end to the other is 1 meter long. Okay. Now I'm using it to pull apart 2 pieces of wood. So I'm doing some demo work, and I shove it in between 2 pieces of wood that are nailed together. Okay. Now it says that I am 0.85 meters away from the fulcrum. So the user is always on the longer end. Otherwise, it's harder to use the machine. So if that's 0.85 meters, and that is going to be the input distance, can someone tell me what the output distance would be? The total is 1. I've already used up 0.85, so this has to be what? So that's right, someone told me. It's going to be 0.15. And that'll be my output distance. So this is on the effort side. This is on the side where something is getting done. Final work is getting done. So I'm just going to delete that. Now how much force do I need to push with? So I am pushing on this end right here. That would be the input force. The input force is my question mark. If in order to separate the 2 pieces of wood, that would be the output force. I need 1,000 newtons of force. Now, if they don't tell you that there's friction, you guys, you assume that there's no friction. And if there's no friction at all, the work in is going to be equal to the work out, which means that the input force times the input distance is going to be equal to the output force times the output distance. Okay, so if that's true, the input force, that's the thing I don't know. The input distance, we said that was 0.85. The output force, that's the force required to push the 2 pieces of wood apart. That's going to be 1,000. And then the output distance, that's going to be the smaller distance. It's 0.15 meters. So if I punch this in my calculator, that is going to be 150. You guys can confirm that. Yep, okay, 150. And then I want to get rid of this 0.85. So I need to divide both sides by that. And those will cancel. And so 150 divided by 0.85, I can't do that in my head. Oh, 176.5. There we go. So you guys, I couldn't actually apply 1,000 newtons of force, but if I use this crowbar, I can apply 176.5 newtons of force. Now remember, that's going to be like 40 pounds. This is like 40 pounds of force. This is like 250 pounds of force. And even if you could do the 250 pounds of force, doing it over and over and over, if you were doing demo work, that might make you tired pretty fast, right? So that's why we have things like crowbars. Okay, so then most people are looking up, so I think most people have finished writing this stuff down. Can we go on to the next problem? Yeah? Give me, okay, I got a bunch of nods. All right. So we'll do one more problem today, you guys, together. And then I'll cut you loose for your 3-day weekend. Although you still probably have 2 other classes. So now this is a little different. I have a box, and I need to push it up a ramp. So I set up a ramp, and I have a box. My box probably has wheels on it, right, just to make it easier. So it says that the ramp is 3 meters long. So this distance is 3 meters. Now that's going to be the input distance. That's a distance that I'm pushing it. It also says that the ramp is 1 meter high. That is going to be the output distance, because that's how high it's being lifted up above the ground. If I didn't use the ramp, I would have to lift it 1 meter. Now the box has a weight of 400 newtons. That is going to be the output force. Now the reason that's the output force is because if I didn't use this ramp, that's the force I would have to apply to lift the box up. Now it also says that this time there's friction, and so the efficiency is 80%. And I want to know, how hard do I have to push So that's going to be the input force. So in this time, we're kind of like back in the real world. There's actually friction. So my friction's 80%. So this time we can't say that the work in is equal to the work out. That's not going to be true. We're going to lose some of our input work. Some of our input work will be converted into heat. And so for this one, it's the efficiency times the work in equals the work out. Okay, so for efficiency, you guys, I don't write 80%. Convert that to a decimal, and so it'll be 0.8. So to convert any percentage to a decimal, I think you guys know this, you just divide by 100. All right, so that'll be 0.8, and then it'll be 0.8 times the input force. I don't know the input force. Times the input distance. That's going to be 3 meters. And that has to equal the output force. Well, the output force is 400 newtons. Times the output distance, that's 1 meter. So we'll times 3 times 0.8. And we'll get the force input times 2.4 is going to equal 400. Because 400 times 1 is just 400. Okay, and then how do I get 2.4 by itself? Well, they're being multiplied. So I will divide. Those cancel out. And I can't do that in my head. 166.6. Thank you. 166.6 newtons. Okay, so if this were 100% efficient, you guys, it would have been 133.3 because it would have been 400 divided by 3, but it wasn't. Some of my energy gets converted into heat here, into thermal energy. So I'm quote unquote losing it, right, to do useful work. So I have to apply a bigger force, 166.6 newtons.